I went to Sizewell B recently. Sizewell B is Britain's only pressurized water nuclear reactor, and it's absolutely spectacular. When you go into the turbine hall, it's like a cathedral to energy. It has two gigantic turbines, which are like giant jet engines, encased in steel, but you can go up and touch the steel, and you can feel the turbine spinning at 3,000 revolutions per minute. Or 50 hertz, which I learned while I was there. Very interesting, I thought. 50 revolutions per second. But the thing is, Sizewell B was finished 30 years ago, and Britain hasn't completed a new nuclear reactor since then. The same story goes in lots of other countries, which built often dozens of nuclear reactors in the post-war era, and then for some reason stopped in the 80s and the 90s. Now, though, thanks to demand for data centers, thanks to concerns about decarbonization, and concerns about energy security, nuclear is back. People are interested in whether we can make nuclear work again, somehow make it cheaper, somehow make it faster, and restart the golden age of nuclear power that we had. So I'm joined today by my colleagues Ben Southwood and Alex Chalmers, both of whom have written quite a bit on nuclear, to talk about why nuclear was so promising to begin with, why it became a flop, and whether it's possible to bring nuclear back. Ben, maybe you could just start us off by talking about what was the promise of nuclear? Why did anybody care about it in the first place?
So nuclear power is very interesting for one reason. Basically, it's like fossil fuels, but just much more energy dense. So a lot of the cost, about half of the cost at least, of producing power with a coal power plant is digging up all the coal, transporting it, burning it, then getting rid of the enormous amounts of waste it generates, and completely put aside the fact that, it causes lung cancer and makes it impossible to see in London in the 1950s. They didn't care about these things that much at the time when nuclear power was coming in. But because you need to use 300,000 times less fuel, if you can get hold of it easily, which it turned out we could, if you can enrich it easily, which it turned out we could, then it could be not 300,000 times cheaper, but you could just get rid of the fuel cost. The fuel cost is basically trivial. It's like 2% of the cost of running a nuclear power plant. So we just got rid of that fuel cost. So what we should have is just a half the cost of a coal power plant, because you've got the same turbines, you've got the same boiling. Instead of burning coal to boil it, you're creating a nuclear reaction by having particular metals in a particular place. But essentially, you're boiling water that turns a turbine. So it's the same thing. You should have stuff that's just half the cost of a coal power plant. That's why the American utilities loved it in the 1950s when they started building them. That's why the British government, through the Central Electricity Generating Board, was interested in the 1950s. And it also came out to be true. So they didn't work it out straight away, but over the first 10 years of nuclear power, it got cheaper in both Britain and the US. And they were building nuclear power plants for, in modern money, about $500 per kilowatt of resultant of capacity that it has, which was what they call overnight cost, but technical jargon. But if you put a recent nuclear power plant in those terms, like I don't know how to pronounce it, Vogtle, in Georgia, then I think it's about $16,000 per kilowatt in modern money versus $500, so about 30 times more expensive. So, and by the way, they were building these in about 4 years instead of 27 years, as Vogtle took to finally get plugged in. So you can see why people were excited about it, right? Like there's a new form of electricity that's going to make it so abundant that we're going to be able to have electricity that's like half the price. And by the way, in the 1960s, the US Army Corps of Engineers, I think, was making this calculation, but I could be wrong there. They judged that in modern money, the electricity was 3 cents per kilowatt hour. So let's say like 2.5p. And I can imagine that's to the end consumer. Yeah. I can imagine, Sammy, that your electricity does not cost 2.5p per kilowatt hour.
No, mine is like 21 pence, 23 pence.
There we
per
go. So we've got 10
hour.
times worse at producing electricity than they did in the 1950s and 1960s. So that's the promise. It started off as potentially the cheapest way. That was like the key thing, is that it was the cheapest way to produce energy. They didn't care about the fact it was green. No one cared about carbon then. Yeah. They did care a bit about local pollution, but not that much. There maybe acid rain when it finally became obvious, but that just wasn't what was on their mind.
And everything went perfectly, and now we have incredibly cheap energy, but it's too cheap to meter, right, Alex?
Pretty much. I don't actually know why we're sat here having a conversation about it. So no. Yes. So I think.
So what went wrong?
Yeah. So I think Ben outlines like gets exactly right when he talks about why people were enthusiastic, and that narrative held through kind of mid to late 1950s through most of the 1960s. But the exact point it begins to go wrong varies by country, but a few sort of common patterns begin to emerge. So one, costs start to rise from the late 1960s, early 1970s, and this happens for a couple of different reasons. One, I think in both the UK and the US, the industry essentially overpromises and underdelivers. It begins moving to bigger and more complicated reactor designs. It assumes that kind of costs will scale linearly. Companies underbid to win contracts in kind of commercially competitive situations. And this essentially doesn't play out. And this begins to erode popular and bureaucratic trusts in the industry.
In what way? So what do you mean it doesn't play out, and how does that erode trust?
So, for example, if you look at the US, it's that like essentially companies promise regional utilities that we will build a reactor in this time to this budget, and they go over time and they go over budget. In the UK, it goes much more spectacularly wrong. So in the UK originally had this design called the Magnox for the first wave of its nuclear program. It built 26 of these in about 15 years, which is pretty spectacular. And then in the mid 1960s, it decides to move to a larger and more efficient design known as the Advanced Gas Reactor. And this unleashes Dungeon SB, which is probably the worst infrastructure project in post-war Britain, where a company
That's a very competitive field.
which is a very competitive field. And it's a really weird story. So they're tendering for this nuclear power station. And Britain had the system because there was no one company that was capable of like building all the components and all the bits and employing enough people to build a power station. So it would tender these out to these competing consortia. And the bid to build Dungeon SB was won by a consortium that was actually on the brink of going bankrupt, that had won it by insanely underbidding on time and cost to build essentially a first-of-a-kind reactor design. They claimed they could build this thing in 4 years. No one had built one at full scale before. The company goes bust a few years in. Huge amounts of the engineering work end up having to be redone. Nuclear inspectors refuse to sign off on the reactor. It finally, I think, having started in the mid-60s, gets switched on in the 1980s, and I think is like running about 12% of the time. So, I mean, the sort of these kind of like white elephant projects like begin to damage kind of confidence in the industry. But there's a sort of parallel story playing out. So you have a degree of kind of hubris and bluster on the engineering front. But at the same time, you have a kind of changing popular and regulatory context. So one of the big changes you see in the 1960s and the 1970s across much of the West is the growth of the environmental movement. So for example, in 1971, the US nuclear regulator loses a landmark Supreme Court case known as the Calvert-Cliffs decision, which means they start having to do proper environmental assessments before they can build nuclear power stations. In the 1970s, one of the kind of big drivers of the early environmental movement is a slightly melodramatic backlash about nuclear waste. And the industry, because it believes that nuclear waste is sort of a fake problem, like you can just put it in some concrete and forget about it, they don't take this very seriously and suddenly find themselves on the receiving end of a lot of sort of popular hurt and popular upset. And then finally, you begin to see a changing kind of regulatory context for licensing decisions and around nuclear safety, which becomes progressively more conservative as the 1970s press on. Some of this is driven by evolutions in the science. So over the course of the 50s and 60s, scientists become more and more concerned about the effects that radiation can have on the body. Like this is embodied in something called the linear no threshold hypothesis, which states that damage and harm from risk from radiation is both cumulative, so it builds up in the body over time, the body doesn't heal from it, and there is sort of no safe threshold.
This is as opposed to a model that says that your body experiences small stresses, but it repairs itself.
Yes.
Like, the difference between drinking 365 pints over a year or in a night.
Yes.
Clearly your body does do some recovery or some processing of the alcohol when it comes to alcohol. The question in nuclear is, does the body do that?
Yeah, it's exactly that. So in their defense, in the 1950s, we didn't really know as much about things like DNA and how the body heals. And most of the evidence and our kind of theories about this developed over the course of it. But we basically knew most of this, including on some of the kind of more extreme, what are known as double strand breaks in DNA. We basically knew this by the 1980s. We didn't know this in the 1950s. But the model we use to regulate radiation has not been updated in line with these scientific developments. In fact, we probably got this right in the 30s. So our operating assumption, like historically, was there was a safe level of radiation, and you could be hit with that about 100 millisieverts S, and you'd probably be fine. Then above that, the risk starts to kind of build up, which was our old assumption. We sort of junked this in the 50s and 60s. And now it's quite funny. I sort of talk to people who work on this, and they're basically saying, if you look at our first, international set of radiation guidelines from 1934, it was actually probably closer to the truth than the model we use today. It's a rare case of us going backwards.
So my question, or I'm curious about the environmentalist movement.
Yeah.
How much are they worried about nuclear waste? How much are they worried about radiation? Or are there other things? What is it exactly in the 1960s, for example, that the environmentalist movement is worried about with nuclear power?
So it's an interesting one. And it's a case where I think a bunch of sort of relatively weak arguments get lumped together, which sort of bulk them out and make them stronger. So some of it was essentially concern or panic about the prospect of nuclear war. And this was sort of an anti-imperialist, anti-NATO thing. And this kind of spilled over into civilian
Because to be
nuclear
fair,
power.
the reactors were being used to produce plutonium in some cases, right?
By the 1960s, everyone had worked out chemicals, so no one was really using them. It turns out that we were doing that because we're using the old kind of reactor.
But the original wave of nuclear reactors built in Britain anyway were done.
Yes, the US nuclear power plants, by and large, were not being used to enrich plutonium to make bombs.
And we didn't use most of the Magnoxes to do that. So the Magnox design sort of emerged from the nuclear program. But I think after Calder Hall, the ones we built were sort of single use.
We had way too much plutonium by now it's still there in a big pile.
Yeah.
One of the things that you highlighted that I'd never heard about before is some of the nuclear bomb tests. So firstly, the organization regulating nuclear power was in fact in the US the same organization that was doing bomb tests and stuff. So the associating
the Atomic Energy Commission.
Associating them together was kind of reasonable. And secondly, some of the bomb tests they were doing were pretty risky kinds of.
Yeah, there were a lot of mysterious sheep deaths in Colorado in the 1950s, and there was a whole panic about strontium ending up in milk in the late 50s. But I think the most notorious one they did was Castle Bravo in 1954, which was done in the Bikini Atoll, near the Marshall Islands, and the wind speed changed unexpectedly, and the bomb generated much, much more fallout than expected. And the US essentially rendered an entire island perpetually uninhabitable. So this island called Rongelap, where they had to evacuate the entire population because ash rained down on it and children went out to go and play with it thinking it was snow.
Wow.
And then got quite ill, and there were elevated cancer levels in the population perpetually. And some of the fallout hit a Japanese fishing ship, the ironically named Lucky Dragon. And the crew found pus leaking from their eyes. And by the time people had realized what had happened, their fish was being sold in Japan. And this triggered understandably also considering what happened in Japan a decade earlier, triggered a wave of national panic and sort of fish being bulk destroyed. So some of these tests did go wrong in a quite spectacular way.
So nuclear has for maybe understandable reasons quite bad vibes at this point. Are environmentalists at what point do they start to worry about meltdowns and things like that? And actually, if either of you could talk us through what actually is a meltdown, what's happening when a meltdown is happening, that would be quite helpful.
I will do environmentalism, and Ben has strong opinions on how real meltdowns are. So we'll leave that one to him.
I think Alex is better on both.
But no. So on I think the fear of meltdowns. I think that, nuclear safety as a concern, I think really became heightened in the 1970s. Partly because you had a series of smaller accidents. So for example, there was I think one at Brown Ferry in the United States, and this is also when the waste conversation begins to get going. Like one of the unfortunate instances you get is like for the UK nuclear industry is Greenpeace in one of its first ever bits of activism essentially catches UK ships dumping nuclear waste at sea, which, as you can imagine, goes down really, really well with the public. And they managed to actually cause such an outcry over it that sort of transport workers like threatened to like boycott the industry if they don't stop doing it. And so, I mean, that's one of the kind of, and the other one with the UK in the mid-70s is, I think it's 1975, although someone will write in to correct me, that the UK plans to build a reprocessing facility at Sellafield so countries can ship their nuclear waste to the UK, get it reprocessed, and then they could theoretically use it again as fuel. And there's this Daily Mirror headline that says, secret plan to turn Britain into world's nuclear dustbin, which again then leads to huge protests. I think Friends of the Earth chartered a train from London to Sellafield, and they held a debate with like representatives from the site on like a football pitch, like next to the power station. I didn't know you could actually charter trains to do that, but like so this actually begins to like generate like quite a lot of public concern, and the industry sort of thinks it's a fake issue. They're like, well, we'll be able to use this to like fuel advanced future reactors. It's basically safe in tanks. And then plans to build sort of nuclear fuel disposal facilities get protested in every community they're like proposed in.
Sellafield, possibly related to what you're talking about. When I was growing up, Sellafield was like absolutely one of the top stories in Ireland. Because it's on the west coast, on the north, up towards Scotland. At the time, the concern was that there would be some kind of accident, and the wind would blow it to Ireland rather than. So it would be it basically was a sort of a moral hazard problem.
It's much like the kind of this concern you got after like Chernobyl in 86 of the wind will blow the radiation line.
Hence the name
there
of
is still like fake German evidence showing that Chernobyl led to effects in Europe.
And hence the name of the film, When the Wind Blows, which is very scary and very good.
And this,
great film.
Yeah, and speaking of Chernobyl, that was, I think, the last pillar that did it for sort of really help the environmental movement was the meltdown at 3 Mile Island in 1979 in Pennsylvania, although that unit is now being apparently revived, which didn't actually harm anyone based on like the best scientific evidence that we have now, but it sort of really fueled the anti-nuclear movement. And then obviously
they had to evacuate the area, did they? Or
I mean, it turns out that they would have been fine not to evacuate the area. They did evacuate the area, but there was also a massive degree of cover-up. This seems, from what Alex has told me, it seems like this is a pretty much standard. These guys are covering everything up, and then hope in the short run, like, oh great, no one's been polarized more against nuclear, but in the long run, everyone seems to come around in the
I think this is exactly right, and I think part of this is about the kind of culture of the nuclear industry in the early nuclear industry, is that lots of the people involved in it had previously worked in like wartime nuclear programs, where the idea that public opinion or public concern was a factor that you had to take seriously just like didn't really occur to them. So I think like this is a consistent theme that you see through the 60s and 70s, is the kind of idea that the public put their trust in the enlightened engineer or enlightened expert or enlightened technocrat just sort of dies a little bit of a death, but the technocrats don't really realize that it's happening to them.
So let's get on to Alara, because a lot of what you've talked about, I think reasonably focuses quite like country specific, but the story that we're telling about nuclear is worldwide, or at least kind of across the West. Like most Western countries, with one or two really interesting exceptions, which we'll get onto, most Western countries experience the same kind of decline in support for nuclear power and kind of rising concern about nuclear power. So why is that?
So I think to be fair, I don't think there's actually that much of a decline in support for nuclear power. In terms of, if you poll people, the decline comes quite a lot later. I think the decline comes after nuclear power becomes slow and expensive, and they're like, oh, it's a bad source of power. I don't actually think that the disasters cause a massive fall off in popular opinion for it, and most of the costs come in before the disasters, which is like, in fact, a lot of the costs come in before Alara comes in. Like a significant amount comes in afterwards.
But let's talk about Alara though. Okay. Explain what does that stand for? What is that?
Yeah, so Alara stands for as low as reasonably achievable, and it's a risk management philosophy that the nuclear industry begins to embrace in the 1970s. It's called a LARP, or as low as reasonably practicable in the UK, but it essentially amounts to a version of the same thing. And this is the idea that risk should be sort of pushed down to, a level beyond which pushing them down becomes, very, very, or like, very disproportionate.
I think that is obviously I agree with that. But I think another way of putting it that is quite useful is if you can afford, i.e., if there are any profits left over after currently in the project plan, and then you can afford a mitigation that will reduce emissions or the risk of radiation emissions to any degree, then you're obliged to do it so long as there is any profit left over. And you can see why bringing this in and then having 2 oil crises led to a massive explosion of cost, right? So like just at the time where wholesale prices are going up massively, and so therefore profits for nuclear power plants in principle are going up massively, they're like, okay, just do all these things. And the nuclear operators end up saying, well, we can, it's fine. Okay, we can take it on the chin because prices are so high. But then obviously afterwards, when the regulations have already kicked in, you can't ratchet them back down. But the key thing I think is it makes profits illegal, or like it makes anything above the minimum profit for it to go ahead illegal. And that means that prices, any potential, you invent any new mitigation, like come up with a new kind of filter, you have to implement it.
Yes, it essentially means that you get punished for good behavior. So any innovation that anyone else makes in safety suddenly becomes like the new flaw, or well, they had an extra backup system. Why don't you have an extra backup system? And you actually see this in how regulation gets rewritten. So the Office for Nuclear Regulation, the UK's nuclear regulator, issues, these guidelines, and one of them is something called the baseline safety objective, which sort of, I won't go into the full UK risk management philosophy, but it's kind of
this is today we're talking about in the present day.
This in the present day, and it's if you get like below this level of risk, you're probably okay, although not guaranteed to be. And they actually said that on like radiation, they've lowered some of the baseline safety objectives further, not because of any change in their risk assessment or the science. Like it explicitly says this in their safety assessment principles. We just think that the industry can do this easily now, so we've just moved the baseline, and it's not in like. Yeah,
and I do want somebody to explain what a meltdown is, because the term meltdown is, everybody knows what the term is, but I think almost nobody can actually describe to you what is happening when a meltdown is happening. So explain that, but also as part of that, what is it that LRA is actually trying to reduce? Is it background radiation? Is it meltdown risk? Is it something else? Is it everything?
So in the UK, this happens in every different country, but I've looked at the UK things a lot of times, so I know in the UK there are
differently in every country. Yeah,
it's basically it's similar in every country. They have like 14 different things they're trying to avoid, and their risks are all different parts of the chain. So background radiation is not like they do have rules for background radiation, but it's so low. Like it's just irrelevant. In practice, the things, and to be clear, that doesn't mean they've never done stupid stuff to avoid trivial amounts, nugatory levels of background radiation. But that's not. But there are also questions of like the percentage chance of a bad outcome happening and multiple bad outcomes at the same time. So the EPR1 has 2 containment domes, right?
Yeah.
And the outer one can take a direct hit from a plane flying into it, but like at the same time that all of their other systems are failing. So it's more and more rare potential circumstances. They're not impossible, but they're extremely unlikely and probably pointless in many different cases.
Yeah. So we're talking about, is it like 10 to the -6 likelihood events are sort of like over.
Well, that would be like 1 in 100,000.
No,
right?
they're up to like 1 in like 1 million or 10 million reactor operating years are the kind of level of risks that we're trying to mitigate. But in practice, like when you're trying to evaluate that level of risk, it's so sensitive to your inputs that it becomes a little bit of a nonsense, which is why nuclear companies often don't actually try and challenge the kind of cost-benefit analysis, because it all feels like a little bit fake, and they tend to just sort of suck up what the regulator asks them to do out of convenience.
And let's be clear. So let's assume. So Alex and I, we talked about this before, so I know Alex thinks about all this stuff. Alex and I have a view that the standard way they measure the health impacts of radiation is incorrect. But let's just take for a second the assumption that it's true. Even if that's true, the baseline standards before we kept escalating them were pretty damn high relative to all other types of power, right? Maybe that's different now that we have particularly safe ones like solar, photovoltaic solar is very, very safe. Like occasionally people die when they're in the factory when they're making it, or like fall off their roof when they're installing it, but it's extremely safe. So maybe there's a safer form of power now. But compared to basically all of the other ones, nuclear power is an extreme, even if you assume we're going to get a Chernobyl every 40 years or something like that, which, by the way, there's no need for us to have a Chernobyl every 40 years because their management was absolutely disastrous. Nothing like that has ever happened in the West. But let's say, even if we assume we're going to get a Fukushima every 40 years or something, Fukushima, I mean, according to the UN assessment, didn't harm anyone through radiological effects.
So talk me through what's going. So if something goes wrong, what happens?
So do you want to explain the meltdown?
No, I think you do it better.
The basic thing that's happening here, right, is that you have rods. I mean, it might be pebbles in a kind of reactor, or it might be there are all kinds of crazy reactor designs, but mostly rods. You have rods. There are moderators with them that are slowing down the reaction. You lift them up and down to speed it up or slow it down based on trying to hit what to keep it at a steady level. If your coolant, which is usually light water, sometimes what's called heavy water, which we don't need to go into that, and sometimes a gas, like in the UK's power plants, we were using gas-cooled reactors. If that escapes out or something, so like that's not being held in there, or it can't get through the system where it gets cooled down, then it might start overheating, or you get a loss of coolant incident because it's broken into or something. And this is, we've had like 3 big reactor meltdowns over time. Or if like in Chernobyl, you do like a crazy test saying, why not let's do an unregistered test of what would happen if we made all the parameters to their extreme levels, and would something go wrong? But you get one of these things, then it keeps heating, and the metal has a melting point, and then it melts. And it's very hard to control after that point because it's like extremely hot metal just melting through everything around it, and then it starts escaping out. And now we can probably just tank that because we've got good enough containment domes. So in actually a meltdown happening without something else really bad happening, probably won't cause any harm in good Western modern reactors. But if you were doing it in the first ones we had, which didn't even have a containment dome, then that could lead to the UK's worst nuclear disaster in 1957. Something like this is happening. It's not quite that actually, because there isn't a full meltdown, but there's a gas plume, and like iodine, radioactive iodine is getting into the gas plume and then spreading all around like a huge area. And then if it gets into the milk, then you don't want to drink the milk because it concentrates in the thyroid, and that causes much higher all those sorts of effects. So but a meltdown is basically just the core, which is made of metal, melting, gets really hot, and because it's a nuclear reaction that's melting it, you can't cool it. Like if it gets past a certain, there's nothing you can do. What are you gonna like? I don't know, get something with really high specific heat capacity, force it through it really. Basically, you have to wait until it just goes for ages. And that's like in the cases we've had, they've just gone for a really long time.
Because so many people, I think of a nuclear meltdown as a nuclear bomb going off. And they imagine there to be a huge explosion, and obviously you don't want that, and you want to keep those very far from the population. But really what's happening is you have an uncontrolled release of radioactive material into the surrounding area. Like really that's it isn't the melting per se. The melting is bad because it breaches the containment area and it releases radioactive material. Is that right?
Yes, although I would hope that if we had a meltdown in one of our modern ones, they wouldn't breach the containment area.
Okay.
But maybe it would.
I think my understanding is that if you stand on the boundary of a UK nuclear site and there's a full meltdown, you shouldn't get it bigger than 10 millisieverts, which is one full body CT scan. So it's not a big deal. Like you can have one of those, and it seems to have no effect on people's health.
Okay, so bring us up to present day. So we've gotten up to around 3 Mile Island, and we've gotten up to Alara.
So here's the interesting thing, right?
We're still building nuclear reactors at this point, right?
Ish. So in the US, they're still ordering loads of nuclear power plants because they're thinking like oil prices are going to be high forever. We're heading towards peak US oil at this point. They don't know what's going to happen in the future. We need something, even if it's really expensive. They don't know about renewables getting good in the future either. So they're still ordering power plants. Then as things cool off and it doesn't turn out to be as bad as they thought with importing fossil fuels, and these plants keep taking like 5 years longer than they expected and coming in more expensive, a lot of them get cancelled, but they do finish off a bunch of them.
So I think 120 get cancelled after 3 Mile Island. So like you do see like a spike on like the charts of international orders in like the US. You see like And
Right.
in
Okay.
1979, they go off a bit of a cliff.
Okay.
The UK is actually already failing by this point. It's failing for the whole 70s. It's gone, and France hasn't really started. That's the
We'll get on to
interesting
France
thing.
in a minute.
Yeah.
Yeah, France is so interesting, but
Just on the UK, I think it's an interesting one because 1979, Thatcher comes in and she's really into nuclear power and she wants to build like a load more of it. So the government's kind of mulling building maybe as many as like, and in the UK by this point under Thatcher decides we're going to junk these gas-cooled reactors. We don't have any of the kind of like residual weirdness about buying American technology that our kind of predecessors had. So they're going to finally switch from like the bad expensive design to kind of the cheap, efficient international one. And then it begins to all kind of go off the rails in the 1980s. So a couple of things happen. So the 80s is when they decide they're going to build Sizewell B, which you mentioned that you visited, but to kind of cool public fears about like building a pressurized water reactor just after one has like melted down in America. They decide to hold this full public inquiry. And the Thatcher government are like, great, this is going to be our opportunity to just defeat all of our foes and all of the environmentalists and all of the haters. We're going to humiliate them with the sheer strength of our case. They allow the inquiry to be defined along these like really, really broad terms. And so the technocrats from like the Central Electricity Generating Board kind of, to my point about being, technocratic complacency, don't prepare for the inquiry very well. When it gets going in public, it turns out they haven't completed reams of the safety documentation. They have to kind of repeatedly file all these addenda. The kind of cost data they provide on how affordable nuclear is kind of nonsense, and the chair says he doesn't believe it. And because the inquiry is really loosely defined, it spirals off into discussions about the ethics of like importing uranium from like Namibia, which is occupied by apartheid South Africa at this time, Aborigine land rights and the impact of the uranium mining industry on them, other countries' reactor designs. The whole thing goes off the rails and takes over a year. And it doesn't, the government just doesn't.
It took over a year to plan a nuclear power plant. How could they survive this?
Yeah. Sadly, it was at that point the longest ever planning inquiry in like UK history. Then to be eclipsed by Heathrow Terminal 5, not that long later. And so by the time they get round to building it, like that has dented faith. And then when they privatize energy in the UK in the late 1980s. Investors begin like picking through the cost data, and they realize that the enlightened technocrats hadn't been entirely honest about how they were cross-subsidizing nuclear from like coal and oil revenue, and the government has to pull nuclear out of the privatization at the last minute, which is this kind of huge embarrassment for the industry, and then sort of plans to then the rest of the PWR program is effectively shelved at that point.
And the US is just finishing the reactors it ordered, but most of them not. But finishing the reactors ordered, but no more. Just like it turns out that nuclear is very expensive. Everyone now discovers.
Yeah.
It turns out that it was a bad idea. It turns out that like we're just not going to do this anymore. And then I think it is the right time to pivot on to talking about France, because this is just the time when they decide, you know what? After this experience of, because at the time they were importing like all of the oil they needed, right? They didn't discover North Sea oil like we did at the time. They didn't have a massive supply of their own like the US. And they thought we just cannot be in this situation again.
It's so interesting. The exact opposite. Basically, the US and the UK, they have high electricity prices. They kind of think, well, we've got a lot of slack in the system, so we're going to regulate this to make it safer. We'll spend some of those profits on safety. France does the exact opposite thing, and so take up the story.
With France, so like France is an interesting one, because initially they start dabbling in civilian nuclear power in the 60s, and it's largely a car crash. They have these expensive like domestic French designs that use natural uranium that are incredibly inefficient, and there are technical problems with all of them. In the early 1970s, they then switched to the light water reactor, and after the 1973 oil crash, they go, we can't handle this. Like we need energy security. And the French program goes really well. I mean, over the course of the 70s and 80s, they build over 50 reactors.
And these are big reactors. And these are like double the size of or exactly 5 times the size of the smallest. UK
they are like quite chunky, for sure. And I think the French have like a few different things going in their favor. Is one, French Fifth Republic, thanks to Charles de Gaulle, peace be upon him, has like a very centralized political system. So essentially, all decisions about nuclear regulation and licensing like taken away from Parliament. The public essentially has no say. You don't get the kind of hearings and inquiries you get in the UK in the 70s and 80s. So
Yes, but I want to push on that because
don't worry.
Because in the UK, we had that system in the 1960s, right? Like, we had that system. We took it away from ourselves in response to the public. So the interesting bit is what you're about to say next, I think, which is how they sustain that system through a massive build-out, despite the fact they were already, like, we had 3 Mile Island in 1979, then they had Chernobyl, which is an actually really bad nuclear disaster in 1986, and they just keep going through all of that.
Yeah,
and don't get too expensive and don't get slowed down.
They were slowing down by Chernobyl. But so I think France, for one, is that like it's centralized, but it also means that nuclear licensing decisions are taken in like relative secrecy. Until 1979, France doesn't actually have a set of codified nuclear safety rules. And there is like no obligation for EDF, France's state energy company, to run any kind of environmental impact assessment. They just like pick sites and build reactors on them that are deemed appropriate. But there isn't really much. There is a bit of a public backlash in a couple of places, but not a sustained one. And the reason is essentially how like French taxes worked. So unlike if you build a nuclear power station in the UK, any sort of revenues that you might get from it through business taxes like immediately go back to central government to like distribute as it wishes. In France, these are retained locally. So if you have a nuclear power station built in your area, like your town council becomes like absolutely minted.
It's crazy how locally this is in France as well. So France has 3 main types of local government. They have the commune, the department, which is roughly parallel to like a UK district council. There's nothing really that in the US, like maybe like a county in the US, and then the region. And the commune could be, I mean, there are some communes with 0 people in them, or occasionally 1 or 2 people in them. Or it can be Paris inside the périphérique of 2 million people. And they range in, but the point is they can be like 1,000 people. So Choose, which is a funny nuclear power plant because it's on, what do you call like a long bit of a country going into another country without being, it's like a salient. If it was in the First World War battle lines, it'd be called a salient. There's a salient into Belgium. They built Choose on the very end of the salient into Belgium. So it's basically in the middle of Belgium, just happens to be connected. But there are 1,000 people in the commune, including Choose. So they've basically not paid any property taxes for 40 years. And it's extremely popular there.
So they get free satellite television paid for by like the local authority.
Yeah,
as well.
My first knowledge or understanding of this came from a conversation with one of our colleagues at Stripe, who was a he's French, and I was talking to him about this EDF build out, and he was like, "Oh yeah, the playground I used to play in when I was a kid was an EDF playground. Yeah, they built that playground, or I don't know if they physically built it, but presumably there was a plaque somewhere saying paid for by the good people at EDF.
Yeah.
So it's funny how much of French society may be just suffused with this kind of background support, background knowledge.
So my little theory, and I'm not sure if this is true, but this is the tidbits of a starting point of a theory, is like, why didn't the French environmental movement take off and stop them from doing this? Because like the UK started in the same position. The US, it was decentralized, but it started with the ability to mark its own homework to basically just put power plants out, ask no one. But there were political competitors who came in and took it away. And I think one possible reason is that if you make it so that the people who would be most likely to give support to those moves for maybe real reasons or maybe pretextual reasons, to use a word that we like to use in Works in Progress pod. But if there are people who might find themselves thinking, yeah, I do really care about environmentalism. I really care about environmentalism. The thing I care about most is environmentalism, which, by the way, will stop this hulking great concrete mass that maybe puts out invisible emissions that kills me. If environmentalism will stop that, it turns out like I have a really strong gut feeling that environmentalism is amazing and I believe in environmentalism. If you don't have an incentive to believe that, possibly that's the reason why it doesn't get off the ground in France. And so they don't ever impose any of these constraints on themselves, which like the public could vote for that. Like it's not like they wouldn't have had to do a revolution to impose that.
And actually Mitterrand was the big nuclear hater in French politics because I think he essentially just opposed it because de Gaulle was into it, as far as I could tell. I could never actually work out a principled reason why he didn't want nuclear power. And he originally, I think in the 70s, campaigned against like any further kind of nuclear build out. Even then, he ended up having to like moderate this position because it wasn't like supremely popular. I think he was kind of assuming there was a big environmental constituency for this, and like found that there wasn't one.
Do you know much about how EDF? And some of our listeners will be very frustrated that we haven't talked about the fact that this was all state-led.
Yes.
So I think we should talk about that, and I'm curious about how important that was in your view.
There are 5 really great nuclear build-outs, right? South Korea, France, Britain, the US, and South Korea, France, Britain, the US, and
China.
Japan. Well, we can count China, but I mean in like developed Western countries, and 3 of them were run by the state, 2 of them are private. So Japan and the US are basically all private, and it's like regulated utilities buying from private companies producing them. And then in the UK, France, and South Korea may even build them themselves. I don't know if you know that, but I don't know if you know the answer to that question. But in the UK and France, it's like EDF contracting from there's a state utility contracting from them. I mean, clearly there's something going on here that, well, I don't know about clearly. It's definitely interesting that it was successful multiple times with a state-led build-out. It doesn't seem to have been the only way you could do it, and it seems more like that having the regulatory environment, like EDF has had more and more trouble over time building out. The UK continued to be a state-led thing while it failed. Like it wasn't taking away the state that led to the failure of UK nuclear.
Yeah.
We took away the state in 1998 or wherever it was, or 1990, I think maybe it is. But the Central Electricity Generating Board was procuring the nuclear power plants between 1952, whenever it started, and 1990. And most of the failure happened during that period, not after 1990.
Yeah, I don't really buy that if Hinkley Point C was not being built, was being built by the British nuclear company instead of EDF, that essentially, I don't think, theoretically, like, but EDF was then paying for Hinkley Point C off its entire balance sheet anyway, so you don't really have like the whole cost of capital thing.
EDF is building nuclear power plants much more cheaply in France than it is in the UK. So you would say it's a test case of the same state-run company, what the difference in the regulatory regime might make between France and Britain.
But also, I mean, different purchasing regime, right? Or like doesn't that kind of support the idea that maybe if we had a domestic EDF, it would do something as well as France's domestic EDF does it?
I'm open to this idea. I think that the other factors, like the fact that we haven't tried to build a nuclear power plant in 30 years.
Let me put the case forward then. So what's really the thing that really seems likely to me is that scale and certainty and doing like lots of nuclear reactors, like having a pipeline of lots and lots of projects, doing the same thing again and again rather than doing this in stops and starts, and knowing that you've got a customer that will pay you. Like all of those things seem to be very, very important factors. Even in the story that you've told about where things went wrong in Britain, one of the big elements seems to be like basically kind of really dysfunctional competition. It's kind of companies underbidding, companies sort of doing things that are not really wise in like their long-term interests, but maybe make sense in some sort of short-termist way because they have to keep the company afloat and they need cash flow or something like that, and they think they can figure out the problem later down the road. The argument for a state-led approach to this is that it gives you certainty, it gives you scale, you know that the customer will still be there, that the government, the one thing about a state is that it almost certainly will be able to pay its debts and will be able to fulfill its contracts. And if the supplier is also the state, then it has much less of an incentive to kind of undercut those incentives. Now, it may have broken incentives in other ways. And I think your point, Ben, is right, that I think it's a good point that basically there are successful models of each and there are unsuccessful models of each. So it's not at all clear that the reason that one, like France, was successful is this factor. But, looking at the specifics, it definitely seems like if scale is really, really important and certainty is really, really important.
So by the way, I don't think scale is that important at all.
Okay.
And I also don't think certainty is that important at all. So like if you look at the other kinds of things we build, like gas power plants, coal power plants, they get better every year, and they get cheap. They're cheap to build, right? And these are built by a completely wide, diverse array of suppliers. And the point is that like everything that goes into a nuclear power plant is except for a tiny, like only a small only a small number of the components need to be like specific to a nuclear power plant. They're all things that you could supply chain up reasonably well if you were able to do that. If you look at the cheapest power plants of all time, they were not copy and paste jobs. They were ones where they just took decisions. So these are ones built in the late 1960s in the US. These are ones where they took decisions on the fly. They did different designs in every case. They had the option of just doing what the previous guy did, but if there was a cheaper way of doing it, they would do that. So they got better every time. Now, I am not saying that if we had a state-run nuclear body, that I would be fighting to disempower it. I just don't think that I think that it would be a mistake to focus so heavily on that. Right now, we have the UK government now is basically building Sizewell C. Like it's got the largest stake in the project. It's funding it now.
Sizewell C being the successor next door to, which I saw as well. So next door to Sizewell B. Yeah.
So the government is doing that. We'll see if it has and we'll see if it makes a difference. I basically do think it could be done really well through the state, and I think we have lots of examples of that around the world. I just think, just as an intellectual point, I think it'd be wrong to focus on it as the only factor that matters. And I suspect if the UK government did it right now, it would help in certain respects. Because if it was taking on the cost directly on its balance sheet, there will become this really powerful stakeholder, the Treasury, trying to keep your taxes down because then we're going to get the money from because they want to ask you for more. That would be like pushing the price down. They might just say, let's not build it. But I think there will be some helpful forces. But I think a lot of the forces would just act on the government. Like we have a lot of stuff that is being built by the government in the UK that ends up being really expensive anyway, like the Lower Thames Crossing, or there are loads of projects that the government builds and they become really expensive. And so it seems it would be, HS2 or Crossrail, like all of these ones are built by the government. They ended up really expensive. So I suspect it can't just be government run, government.
Yeah, I agree. Like one bit of the government is really, really good at tying the hands of another bit of the government. And we also actually see this historically. So, for example, British nuclear power stations through the 70s and 80s will run with significantly lower capacity factors than their US peers because, well, individual power stations weren't profit centers. They were part of a kind of big, sort of nationalized kind of energy system. So the people running them had no incentive to invest or learn how to do better preventative maintenance. Didn't really kind of have much of an incentive to figure out what are the gaps between maximum potential output and actual output. So when they were forced to do this in the 1990s because they were kind of taken out of the nationalized energy system and put in their own company, even though it was state-run and everyone was watching them, it turned out that they could eke out all these performance improvements they simply sort of hadn't bothered doing before.
And it was the equivalent of adding 2 new reactors in the late 90s when they professionalized the management of the existing stock. But as you say, that was done under a different state body.
It was done under a different state body, but when the industry's feet were being held to the fire and there was an intention to eventually privatize it again.
I mean, what I would take from that though is, and I think you agree, is you can have well-run state organizations and you can have badly run ones, and there's the bigger difference is well and badly run.
Yeah.
And I think that's what we see in
I think it's about incentives, and with both Hinkley Point C and Sizewell C, we got the incentives sort of catastrophically badly wrong.
All right, well then let's bring us up to Hinkley Point C and Sizewell C,
Sure.
because then we can move on to the present day and what we do about it and things like that. But let's finish the story of global nuclear with a kind of special twist or special focus on Britain. So we do Sizewell B.
Yeah,
it's great. It's amazing. Pretty expensive, I think, by historical standards.
$6 billion in modern money. So the prices were beginning to climb for sure.
Then we don't do anything for 15 years.
Yeah.
And then Hinkley Point C comes onto the agenda. Talk to me about that. What happens with Hinkley Point C?
So Hinkley Point C kind of comes up in essentially the late 2000s. So 2007, 2008, we've committed to these ambitious climate change targets. And so we suddenly decided, actually maybe nuclear power would be, some of our nuclear power stations are beginning to be decommissioned by this point, some of the old ones. And we're like, well, maybe we should bring some of this capacity back. And so the government sort of publishes a white paper saying nuclear's back, but we don't want to subsidize it. But if anyone else would like to pay for a nuclear power station, here are some, sites that would be nice to plonk them on. One of which is Hinkley Point C,
because it's already got grid connections and things like that.
Yes, it's already it's because it'd been the site of two Hinkley Point A and Hinkley Point B already. In fact, I think pretty much all the sites they outline as potential ones former nuclear sites of one sort or another. And then EDF proposes this design, the European pressurized reactor, which it was already trying to build in France. And the EPR was essentially a product of Chernobyl. So France stops building new nuclear power after 1991, partly because like the public mood shifted a bit, but primarily because they built so much nuclear capacity that they didn't need it. Like they were actually a lot of their plants were like running below their theoretical capacity because they had like too much energy. So they froze a nuclear build in 1991. 2004, they decided to try and bring back nuclear power, but with a much warier public. So they team up with the Germans to design the safest reactor ever, which has and it's built to Germany's very, very, very strict nuclear safety standards. So it has like insane amounts of redundancy built into it, some of the most advanced safety systems ever. But it's an incredibly sort of complicated, convoluted design. A lot of nuclear engineers sort of wince when you talk about it because they consider it such an aberration. And EDF proposes to build one of these. And they won't build it without subsidy. So like we're not taking on that kind of risk. So it goes through the UK's nuclear approvals process, which has become incredibly conservative in the intervening period. They demand several sort of crucial changes to the design versus the French reference design that's already being built at Flamanville, which itself runs over budget because the design's so complicated. And then essentially, they significantly increase the amount of concrete required, the amount of steel required. They demand a backup analog control system, which means they have to they have to actually design one of these analog control systems, which takes 12 years. So they build in all this additional complexity. And then EDF goes, yep, we'll do all of this. And then we agreed a sort of fixed price at which we'll like buy energy from them in the future.
Same way we buy or we pay for wind power and solar power in the UK. Yeah.
But because I think they reached the financial settlement with us after we've asked them to make all of these changes, they essentially have no incentive to push back on any of them because they end up making a loss on it, but they can push a lot of the cost back onto the British taxpayer. And the CFD, we agree on Hinkley Point C, I think is more expensive than the UK. Higher than UK retail energy price has ever been, apart from briefly during the Ukraine shock. So we agreed to buy energy from them very expensively. And they then build a very, very expensive power station that is running several years behind schedule already and is set to be the most sort of expensive power station of all time built anywhere in the world ever, and should appear at some point in the early 2030s. So essentially we concluded that like nuclear would always be slow and expensive, and like essentially with the complicity of the industry of like turn this into a self-fulfilling prophecy.
And to be fair, while some countries have done better in that no one's done as badly as Hinkley Point C in cost or as Sizewell C will be, I gather that the Finnish, who are pretty good at building nuclear power plants, are still building their most expensive ones ever. And the French obviously are doing that as well. And then famously, the US took 27 years to build their most recent nuclear power plant, I never know how to pronounce it, Vogtle. And that's also extremely expensive, although not quite as bad as ours, but extremely expensive. This was happening everywhere, but we were the worst.
It's also not been happening everywhere. So if you go to like South Korea or the UAE, like they managed to build, I think the South Korea can build nuclear power at a sixth of a cost per kilowatt hour versus us. I mean,
per kilowatt, per kilowatt of output,
And China's reported, I mean, I don't know how much their numbers that they put out are exactly accurate, but they're reporting roughly similar costs. And to be fair, several developing countries or countries that have quite low wage rates are reporting low costs as well. But I don't know how comparable they would be to the UK.
I mean, China actually did build one EPR. I think they managed to build it for $3 billion.
Who did they build it with? How did they get the design?
I think they just licensed it.
No, they did a joint venture. It was a nuclear technology transfer venture by a plant.
So it was still China's worst nuclear build, and basically, they ditched it.
Some countries survive. Like Japan was actually still doing pretty well in both speed and cost until Fukushima, when, in my opinion, they significantly overreacted since then. But that's problem since then. China, South Korea, a few other cases have managed to keep costs low. Russia hasn't been as bad as the West. in its cost explosion. But it is a roughly general story. And the US and UK is very similar story, albeit, it's so funny how parallel it is, given that we had a Soviet style planning system and they had a private competition system, albeit with regulated private utilities. But roughly the same story, roughly the same causes. Although it's complicated, obviously different between countries. That gets us to now. That gets us to now a world where everyone believes that nuclear power is destined to be costly and slow. And no one is, very few people are optimistic about it.
Okay, so we're up to the present day. There's another version of this conversation that we could have done, or we could have framed this in a completely different way, which is solar power is really promising. It seems to be dropping in price by an extraordinary amount. It's already proving to be really, really cost effective in some parts of the world. Sub-Saharan Africa, it allows places that are not really connected to a decent national grid to kind of leapfrog that need. And you're now getting solar plus batteries providing kind of increasing amounts of electricity in some developing countries, and it's becoming more and more cost effective in places like the United States, especially in the Southwest. So, why should you care about nuclear power if you are optimistic about solar? And Alex, I would love to hear, why should you not necessarily be completely bullish on solar. Before we get to that, I'll give the kind of solar optimist case for nuclear, which is, I think there are kind of 3 or 4 elements to this. The first is you can never be certain about anything. Like learning curves, a paper came out recently that showed that learning curves in terms of cost reductions, they're not predictive of future cost reductions. So you can't be sure that solar will continue or batteries will continue the cost reduction trajectory. They might, and it'll be absolutely brilliant if they do, and I really, really hope they do, but it would be a really bad idea to just assume that they will, because if they don't, you're in trouble. The next is there are just some parts of the world where solar is very unlikely to be useful in the near future. Britain is clearly one of them. Some of the Nordic countries are. Now, obviously, Norway has a lot of oil and gas, and it has a lot of hydro. Sweden gets a lot of hydro from both itself and from Norway. But there are parts of the world that just will not be able to rely on solar, barring a much, much bigger breakthrough than anything anybody is sort of saying is imminent in the near future. Another is that nuclear can be used for things that solar can't be. So nuclear reactors generate a lot of heat. Fossil fuels are good at generating heat. Solar is not that good at generating heat. It's not. I'm not saying it's not possible, but a nuclear reactor is directly, as Ben said at the beginning, a nuclear reactor is like a fossil. It's like a fossil fuel way of producing heat to begin with that you then convert into electricity, rather than solar, which would be converting electricity into heat. So those are the kind of 3 sort of objective reasons. I think the most promising reason, or I think the most kind of compelling reason for me, is that we've already done this before. There is no technological breakthrough that is needed to get cheap nuclear. There is a political or policy breakthrough that's needed. Now, you might very well think that that's a silly waste of people's time. Now, people in San Francisco and California basically kind of take political constraints as fixed, and that's a really smart way to act, right? You can make a lot of progress in the world by taking policy constraints as fixed and building around those things. But there are people, and I think of us as being among them, and there are lots of other people out there who can, in fact, change policy, or who can at least try to change policy. And if those people, who are probably not going to set up a really great energy startup or a really great startup, well, maybe we will. But if those people can try to fix the regulatory side of nuclear and return nuclear to what it was, say, 50 years ago, then that's a really, really great way of reducing electricity costs without a massive opportunity cost, at least in energy. Maybe it has some opportunity cost elsewhere. I don't know. So I think that those are the reasons that, even if you think solar, and lots of listeners, I think with good reason, will feel really, really optimistic about solar. But dismissing nuclear and putting all your eggs into the solar basket, I think, has a lot of drawbacks. But at the same time, I wouldn't say that you should put all your eggs into the nuclear basket.
Yeah.
I think that would be a mistake as well.
No, I completely agree with all of that. And my view is, as probably the resident solar skeptic at Works in Progress, that if other people want to raise money and build companies trying to crack long duration battery storage, they have my wholehearted support in doing so. Where I get nervous is where, as you see in places like California, public policy begins to run ahead of the technology. And even somewhere like California, solar capacity factors drop below 10% for extended stretches of the winter. It's how big a battery storage system are we going to build?
Compare that to their summer capacity factors.
I-
About 30, is it?
So it depends where you are, but it can be into like the 20s, I think. So
So it's a variation of 3
yeah,
times.
so how big a battery storage system are we going to have to build, or are we going to have to build it all in one part of the state and build, sort of huge, sort of high voltage cables? Like these things are theoretically soluble, but they're not cheap. Or go to the northeast of the US, where solar capacity factors can be at 4 or 5% in the winter. You're seeing gas plants being taken offline and replaced with solar. And as like this to me seems like a little bit of a disaster in the making.
I will say one thing in favor of our American friends
Yes.
when we discuss this question is that, so as Sam said, one of the things that is relevant in this is that the UK is probably a place where solar is going to be, even if nearly everywhere in the world is has a good time, our latitude is not very good for it. So we're intrinsically, we find it less exciting just because although it may help everyone else, it's going to help us less. Maybe we should migrate to the sun as we should.
Yeah.
Perhaps we always should have done. But another feature that makes it solar better for some countries than others, especially the US, is that if you don't care that you're going to burn fossil fuels at the rare times when they're off, like if you're very relaxed about that, then the cost of renewables is just much lower, right? Like if you have gas plants can be booted up quite quickly at relatively low cost. You can just kick them in when you have any shortfall of solar, even if it's like a cloud that's unexpected. If you're willing to keep that capacity up, then and you're willing to use it, then solar can be much cheaper. If you are committing to a world where you're not willing to do that and you're closing down gas power plants and you're not using them for the backup, then it's going to be much more expensive. And so in a world where you can only do if you're trying to reduce carbon emissions towards zero,
which I feel like seems most people who even in the UK the goal is 95% renewable production of or carbon.
Is that what Clean Power 2030 is now?
Clean Power 2030 is 95%. I think basically I don't think anybody is seriously arguing that it should go
really
to zero.
Strengthens the case for renewables and solar in particular. That said, Brian Potter, which I'm sure many people listening read his excellent blog, but Brian Potter did a good analysis of like how much of the US's energy could solar supply, and it started getting quite expensive, above 60% on like today's technology. Obviously, a lot of this depends on what happens in the future. If in 10 years' time the curves continue the way they've been continuing today, then that might not be the case. You might also be able to you can imagine a world where if things get sufficiently cheap that you can overbuild the UK enough that it's very hard to imagine given how little sun there is in winter, but you can imagine a world where that happened. I think we would need like 20 batteries per person for that. So
I think we sat down and tried to do the maths on this once, and I think
it's like trillion.
I think we had. I think we came up with something like a £4 trillion battery storage system that we.
But yes,
I mean, £4 trillion under current prices, though, right? Like the premise here, and the premise here is that prices fall exponentially, or prices fall incredibly significantly, as they have already. Like battery prices have fallen a lot, not as fast as solar, but still very, very fast. And if that continues, then it might not be as crazy to do this. Like, I don't think anybody is really proposing to have battery storage to cover a country's needs over like 3 or 4 months of the year or something like that. I think that's no, that's a bit of a straw man. But I think it is reasonable to imagine a world where this moving target is moving in the direction that it has been moving and continues to move in that way. There are really big economic incentives. I don't know enough about battery technology to say whether there are like really unsolvable problems ahead. But I don't think that it's crazy. But yes, you do need a lot of gas backup in the system.
Sometimes you come up against technological hard walls. Other times you come up with just new ways that are totally way better than the previous things that you did. And you don't even need to keep improving, lithium-ion batteries or those kind of.
You
invent the new
kind, right?
Like Austin Vernon is trying to build. You heat up some dirt, and then that stores your energy over the year. That could be the answer. I don't know. So I'm completely open to that stuff. I think that we'd be, like you said, it's probably foolish to bet completely on it. And if we made it so that we could build nuclear power as quickly and as affordably as South Korea, then there wouldn't really be this either or question anyway. Like China builds loads of nuclear power plants and also puts loads of solar in. I don't.
That's
and,
the,
and
I
loads
think
of
I think
batteries
that's the
in.
key
It's like
point,
not
right?
really a.
There
It's not really a
isn't
trade-off.
there isn't actually an opportunity cost.
Yes.
That's
Yeah.
the point, right? Like
We just
if
have
there was
more
if there was
energy.
an exactly if there was an opportunity cost, then this would be really hard and a very very like interesting tricky question. I would probably end up falling on the nuclear side, I have to admit.
Yes.
But there isn't an opportunity cost here. There
Unless it turns out you'd be an amazing employee of a renewable energy company, and then there's a huge opportunity cost.
or if I'm actually thinking about it, like maybe permitting would be, the opportunity cost is for people who are working on cheaper nuclear is like, can you make it cheaper to build or deploy like solar grid connections or like general electric grid connections? So like maybe that's where
fixing the
there's an
energy
opportunity
market.
cost.
Like, to be honest though, those are really, they work well together. Like if you fix the energy market you could kind of see it all as a fixing the energy market thing, which would benefit solar and also nuclear at the same time.
So what's the what's your model of what a successful like next 5 years looks like, or next 10 years looks like for getting cheaper nuclear?
So the one thing I think may just happen, and it may just be that we're a sideshow to this and it's just going on, is that it used to be that the costs of expensive nuclear power were spread very finely across the country, or the benefits of cheaper nuclear power would have been spread very finely. Everyone gets a few pennies off their bill each watt hour or whatever, and it takes a long time to come about, and you don't know exactly. You can't trust that it's actually going to come about. Something else might happen in the way, and so it's been hard to coalesce a movement in favor. You can get movements to come in favor for really dispersed benefits, but it takes a while. You have to really build them up, and we haven't really been winning the people who have cared about these things. But suddenly, with AI data centers, like this week, Meta signed a 6.6 gigawatt deal with a bunch of nuclear providers to, over the next 10 years, build like 6.6 gigawatts. So like the equivalent of 5 normal size nuclear reactors, or a bit more than that, whatever. That suggests that the benefits are now of cheaper power are becoming very concentrated, especially in the US, where there's this huge investment in build out. If you have very concentrated benefits, you can imagine that if you're Meta and you're paying, say, 5 times more than what you could be paying for this power, you suddenly become fairly powerful advocate for showing the benefits of this change. And you could, by capturing those benefits, you can become this like, try and work out who are the blockers to this. How can I spread the benefits with these blockers? How can I make there a broad coalition for change? Who do I need to fund? All those sorts of things. They might mess it up. They might not necessarily succeed. But if all of the 5 biggest companies in the US are advocating for cheaper nuclear power, that might be enough to make it going. Now, bit more worried about the UK.
Yeah, that's where it gets trickier, is that we don't quite have that same like potential lobby emerging. But I think we have other reasons probably to be hopeful. So, for example, towards the end of last year, a review that the UK government commissioned was published, and it came out with a relatively punchy set of recommendations about bringing the cost of nuclear down. So, for example, streamlining some of the very time-consuming approvals processes that exist. So, a developer doesn't have to go to like 4 different regulators to like determine the same issue. Removing some of the incentives that make it really, really easy and really cheap for people trying to sabotage development to sort of bring spurious legal claims, and also then remove essentially directing regulators not to kind of mitigate and demand gold plating for these trivially small radiation doses that force the installation of extra filters. So like some of these measures you can imagine bring down some of the costs of these like big UK nuclear mega projects. And I think the other encouraging thing we're seeing is that a lot of European countries are now beginning to look at reviving their nuclear programs. So, for example, Sweden is exploring building SMRs. Hungary, Czechia, Poland are all kind of have nuclear programs that are going ahead. Romania is weighing up competing options. Denmark is looking at lifting its 50-year ban on new nuclear power. So, there are these kind of, they are these kind of like green roots of hope. I mean, in my view, ideally, to keep the statists who are tuning in happy, is that it would make much more sense just to have European-wide coordination on SMR, so you don't have like 9 parallel supply chains being built by all of these different countries.
Small modular reactors are interesting because My understanding is that
Yeah.
there is a significant trade-off in efficiency the smaller you go.
Yeah.
But you may have basically two countervailing forces. One being you might be able to get kind of one and done regulatory approval for a small modular reactor
Yes.
that you can't get for a large scale nuclear reactor. So you get like sort of regulatory economies of scale from that. That's uncertain. Most countries, I don't think any country has like finalized how it's regulating these things, but that would be a way that it could be really nice. The other is if they can be mass produced in factories and they can be assembled kind of relatively easily or relatively kind of straightforwardly, then you might get the kind of learning curves that you get in a factory that solar has obviously benefited from, and like most manufactured goods get to benefit from. I mean, that does seem somewhat promising,
Yes.
but it's definitely a kind of second best to getting big scale reactors cheap. And like, is that right, or do you disagree?
I think SMRs are inefficient versus the platonic ideal of the gigawatt scale reactor, but we never build the platonic ideal of the gigawatt scale reactor. So if like we were building like big nuclear projects efficiently, I think that the trade-off would be much bigger and much more obvious, but we aren't currently operating in that world.
There are some things where having small reactors would be really cool.
Yeah.
Like there are a lot of big ships.
Yeah.
They basically want like a steady amount of power.
They emit a lot of carbon as well.
Yeah, they emit, they're burning loads of kerosene or whatever it is they burn, diesel. We could just, like 20 megawatts, that would do them forever.
Yeah.
For like 100 years of power.
And they could stay at sea all the time.
Yes.
That would be nice.
Yeah, well, like nuclear subs, right?
Yeah.
So yeah.
Nearly all the time.
Yeah, there are a lot of things like that, I think. Also, you were saying about process heat earlier. There are some things we just want heat for rather than we want high temperatures. Now, most of the nuclear power plants we have work with pressurized steam, right? Or pressurized water or pressurized, sometimes boiling water or steam. That's sometimes good, but it's not going to like give you the 1,000 degrees or like 1,500 degrees or 2,000 degrees you want to use in lots of. But there are some designs that all these advanced SMR. I mean, they don't exist yet. So like no, I a lot of times something that really annoys me is when you read copy about SMRs. Like copy is the right word because it's like kind of ad copy. Like people are writing about trying to promote, but they'll often say like this SMR does X. Like no, you mean the design is designed to do this?
Yeah.
Like it doesn't exist anywhere. You can't tell me that it does this. But in principle, especially if we're starting from square one on regulation, there are a lot of design types that might be cool that we could run them with like much hotter coolant. Much hotter coolant means that we can have higher process heat. We can use for like lots of, so you could have this in principle 20 megawatt reactor that powers all the electricity that a plant needs, but also does its heat. Yeah, because converted to electricity is often better, but it just has its downsides, right? And why have the downsides if you don't need them?
That's what I find really interesting, and I am like genuinely unclear as to how much of the kind of the industry question or the industry problem can nuclear solve? Because obviously, but not obviously, but like electricity does top off at a certain heat level. It's like 300 degrees or something like that. I don't know if it can.
I think the arc furnaces can get significally hotter than that, but they definitely can't get as hot as a blast furnace.
Yeah. And maybe it's just the case that we just have to keep using fossil fuels for those things.
Yeah.
Maybe that's fine. But perhaps nuclear does have this like extra thing about it that other clean sources of energies don't have.
I suspect that what we should be doing if we take climate change seriously is mitigating all the stuff that's cheap to mitigate and electrifying it, and then building loads of clean energy so we have abundant clean energy. And then we'll find like the 5% or the 10% of things where it's like, it's quite costly to do this. Like, is it worth doing it? Could we not come up with some way of sucking carbon out of the atmosphere? Or like, have we gone far enough and the natural feedback mechanisms are going to solve this problem, or whatever it is? But you can imagine a world where, okay, it's expensive currently to extract carbon out of the atmosphere, but you can imagine a world where that was less expensive than just getting rid of blast furnaces and switching them to. I mean, actually, I gather that arc furnaces aren't that bad, but there are other cases which cracking plants or whatever that I don't understand this stuff very well. There's definitely potential there. I think SMRs are probably better than just a regulatory get around because of the scale thing. Like, scale is just good.
Mass production scale, you mean?
Yeah, exactly. Yeah, I think, but unproven. There are a few plugged in the world that count as small modular reactors. I'm always doubtful on to what extent they're actually modular, and
Yes.
are they really that small? Like the ones I like are like Last Energy's design is really actually quite small. It's like like a few shipping containers. Whereas some of them are like a couple of warehouses. It's like, yes, it's smaller than Sizewell B that you mentioned.
Well, Rolls-Royce SMR is...
It's not actually an SMR.
It's like
the
two
SMR,
football fields, right?
Yeah, it's huge. I mean, the SMR definition was traditionally like 300 megawatts or under, and it's over 400, and it's not modular.
Yeah.
It's neither small nor modular, but it is a reactor, so we can't do the real joke.
Yes.
So I'm reasonably... I think that it would be it's foolish when people say, look, you're working on a problem that is well, yeah, it would make the world better if you solve that problem, but there is another and more important problem, because like there are a lot of problems, and we shouldn't all work on the most important problem. We still need someone to make our shoes. Like, that's not the most important problem in the world, but it would suck if we didn't have shoes. And there are loads of things like that. So I think it's foolish to say like you shouldn't try and solve nuclear costs. I'm hopeful that it will solve itself now that there are strong stakeholders in the game, but that's not a reason for complacency.
Great. Before we wrap up, is there anything that we haven't talked about that you'd like to talk about?
So I don't want to go on one about this, because it's definitely a topic that people who talk to me have heard too much about already. But I think that is the fear of radiation is very exaggerated. And I think there's a really interesting question as to why people have a fear that's so out of line with what I think the evidence clearly shows. And I'm coming up with some theories right now, but that's not what I want to talk about. Just the evidence against there being big harms from the normal levels of radiation that you might be expected to experience if you were near a melting down reactor, for example. So, like, take Chernobyl. Chernobyl, according to, I think it's the UN Radiation Committee's report, they reckon killed about 200 people total. Of those, most of the deaths are estimated. There's no like proven link, but they think probably 200 people-ish died of raised cancer rates due to infected milk and things like that. There are about, 20 first responders who died?
Yes,
28?
Something like that.
Now, those guys had doses of, we often talk in millisieverts, that's jargon. Let's think of it in terms of CT scans, right? Because a full-body CT scan is the most radiation that someone would normally experience in their life, unless they had like radiotherapy for cancer, but that would be focused in one place, so it wouldn't have all-body harms. They're 10 millisieverts. So these guys were getting, like, within hours, hundreds of sieverts. So like hundreds of thousands, so like, thousands of CT scanners. And they died like pretty quickly within hours or days. Then no one else, anyone who was nearby, people who are like, no one else has any proven harm except for higher cancer rates like decades later. And this is the worst nuclear disaster ever. You can look at other examples that are pretty, like, these are the extreme cases, but I think it's worth looking at the extreme cases rather than the cases where we try and detect an effect from really tiny amounts, because I think that the statistical techniques are all like kind of making something out of nothing there. So other crazy cases, so Hiroshima and Nagasaki, right? Obviously, their main effect is they just directly killed loads of people. But also, if you weren't killed by the direct blast and you're within 1,200 meters, you got enough dose to have a detectable health effect. Am I right? 1,200 meters?
Yes, roughly.
And then beyond that point, they have they collected data on loads of people through their whole life. Beyond that point, no detectable effects. And these guys got quite a high dose in quite a short period of time.
And they found like no like heritable effects either. It's like the descent, you have this idea. So you often hear about people about Hiroshima and Nagasaki go, well, you hear about all these babies who were born like with deformed like.
I think there were deformed babies, but those were people within 1,200 meters who were pregnant at the time they were hit by the blast. But there were no like delayed effects.
You have people with this imagination that were like waves and waves of them.
So these are really extreme cases. Yes. So in the Hiroshima one, they got 100 CT scans in a second, right? So that's like and they had no detectable effects. That's like the edge case. But we can go. Like, there are loads of different examples looking at stuff like this. So there's this really horrible case of, in the 1920s, people used to like to have glow-in-the-dark watches. Yeah. And the only way they knew of doing it at that time was to get radioactive radium paint, paint it on the dials. And there were women, it was all women, who licked brushes with radium, and they were told to lick them for the first 8 years, and then they realized that it was making these women's jaw fall off from like basically inside. Taking the radium inside led to much higher doses than being near the radium. The radium wasn't necessarily a problem when your skin could block it, but when it was inside, it was causing alpha emitters.
Yes.
Cause lots of damage when they're inside. They stopped doing that. Anyway, they tracked all of these women, and you can see a straightforward curve of when they got to, is it 100 millisieverts a day?
Yes, that sounds right.
So 10 CT scans a day. The girls who were getting the women who were getting a dose of 10 CT scans a day had like long-term, very noticeable cancer effects. But when they were like 5 CT scans a day, they weren't getting any noticeable cancer effects.
Yeah.
And there are many, many, many studies like this on extreme doses. There are really crazy ones, like the CIA's. Is it CIA? Did the nasty one
Is this where they just injected plutonium in like terminal cancer patients to see what happened?
Yeah. So they found a bunch of I think they're all men who were dying of cancer. And they were like, okay, let's see if we can kill them quicker by injecting them with loads of plutonium, because they're going to die anyway. And they didn't kill any of them. One of them didn't have cancer. He was misdiagnosed. Also didn't affect him. He lived till 84. And they gave him like hundreds of doses of like a dose they were deliberately trying to see, can we create an effect here? And they weren't able to do it. Now, I'm not saying radiation clearly, it kills you instantly if you go into Chernobyl. There are loads of doses. Some of these doses, like the Hiroshima guys, I am very surprised by that. And I would have thought that 100 CT scans in a day would be enough to affect you long run. But the point is, actually, I think the evidence is that the harms of radiation are massively overstated. And in fact, even a meltdown usually doesn't cause significant health harms. Like, we should work to prevent meltdowns, but we should also live in a world where a certain number of meltdowns is an acceptable cost of doing business, so long as we have reasonable protocols to deal with them, which we do. So anyway, that's just like a bugbear of mine, is that people massively exaggerate the potential harms from radiation.
Well, very interesting. Thanks very much, Alex, Ben. Anybody, if you're listening or watching and you found that interesting, I really, really recommend Ben and Alex's writing. Especially Alex has written tons for Works in Progress on nuclear. The French nuclear build-out to me is the most interesting and absolutely mind-boggling, and makes me a real kind of Francophile, or more than I already was a Francophile. And you've got more to come.
Yeah.
So lots to be excited about there. Thank you very much for listening and for watching. If you've enjoyed this, check out worksinprogress.co/print to order and subscribe to the print magazine. Next issue is going out very shortly. And thanks very much for listening, and see you again next time. Bye-bye.